Good morning. I welcome you all to this session of fluid mechanics. Now last class we were discussing about the velocity profiles in a Couette flow, an exact solution of Navier-Stokes equations. Okay, let us continue the discussion now. We see that in Couette flow in the last class we discussed the velocity profile as a function of y in this fashion. This is y direction, this is x, one of the plate is moving. Now y by h plus alpha y by h 1 minus y by h, where alpha is the non-dimensional pressure gradient, which is defined as h square by 2 mu u infinity minus dp dx. H is the distance between the plates. Now you see from here that when alpha is equal to 0 is a simple case, then u by u infinity is y by h. This is the curve which is plane Couette flow or simple Couette flow as I discussed earlier. So from 0 at this plate which is at rest to u infinity linearly. The velocity varies. Now before going to find out the velocity profiles for different values of alpha as parameters, we discussed the different regimes. One regime is alpha greater than 0 when dp dx is less than 0. That means this is a favorable pressure gradient, the pressure decreases in the direction of flow. And another regime is that alpha less than 0, that is negative value, which is associated with the positive value of the pressure gradient. That means pressure increases in the direction of flow, which is the adverse pressure gradient situation. Now one thing was noticed that this curve has both a maximum and minimum, and it is found that when alpha is greater than 0 for negative pressure gradient the curve shows a maximum, while alpha less than 0 for a positive pressure gradient the curve shows a minimum. And for maximum and minimum condition was satisfied by making del u del y 0, and we arrived at a condition with respect to y by h half plus half alpha. This we already recognized the last class. Now here we have seen that when alpha greater than 0 but less than 1, that means in this regime of alpha we have seen less than equal to 1, y by h if you put here is more than 1, that means more than the flow regime, beyond the flow regime. So therefore in this case the maximum velocity is u infinity, though a mathematical maximum may not exist. But exactly at alpha is equal to 1, we get a mathematical maximum at y by h is equal to 1. That means at this point there is a mathematical maximum. That means that alpha is equal to 1, the maximum value of the velocity is u infinity, because here the velocity is u infinity but it shows a maximum value. That means that del u del y or du dy is 0 here. That is the curve alpha is equal to 1. And we see that alpha greater than 1, that means in this regime alpha greater than 1, or we can write this way, alpha greater than 1, we see that y by h is lower than 1, alpha greater than 1, from this equation y by h is less than 1. So therefore the maximum velocity occurs somewhere here. So that has to be more than u infinity, because here the velocity will be u infinity. So it will be more than this, then it goes on decreasing. This is the value curve for different alpha 3. Similarly, it is found that in this range when alpha less than 0, it has been found that so long alpha is greater than minus 1, greater than is equal to minus 1, then the minimum will be found at a distance lower than 0, less than 0, which is not feasible. So therefore in this regime, that means alpha greater than is equal to minus 1, the minimum velocity is the 0 velocity. Exactly at alpha is equal to minus 1, we get y by h 0. That means that alpha is equal to minus 1, we get a 0 gradient here. That means a minimum condition, and the minimum velocity is 0. That means this will be alpha is equal to minus 1. So when alpha is still less than minus 1, that means minus 2, minus 3, if we put here we get a value of y by h greater than 0, which means slightly away from this fixed plate. That means it comes in the flow region, a minimum velocity comes, and that minimum velocity will be lower than 0 velocity, because here the velocity will be 0, which means a negative velocity appears somewhere here, which implies a reversal of flow in this direction. This is for alpha is minus 2, alpha is minus 3. So this is precisely the velocity distributions characteristics that we discussed yesterday. Now we want to see the nature of the shear stress distributions. Now you see, if we write the shear stress from here, tau yx is simply mu du dy. So mu u infinity. So if you make du dy, it will be 1 by h plus alpha into, it will be 1 by h minus y square 2y by h. So simply this is the expression for the shear stress. Now if we are interested for shear stress at two walls, then first of all I write tau xy at y is equal to h, then what we get mu infinity 1 by h, sorry 1 by h. So, if we put y is equal to h, 2 by h, 1 by h, so simply minus alpha by h. That means we can write mu u infinity by h into 1 minus alpha. So, from here we see clearly one thing, that when alpha is equal to 1, then this is 0. So, you see when alpha greater than less than 1, when alpha less than 1, alpha between 0 to 1 in this regime, this shear stress is positive. Alpha is equal to 1, shear stress is 0, this curve. So, from the curve itself it is clear, and when alpha greater than 1, the shear stress goes on changing its direction. What does it mean? That means when alpha is equal to 0, there is no shear stress. That means the plate, moving plate doesn't experience any drag force. Obviously, in that case the favorable pressure gradient which is imposed in the flow at the value of alpha is equal to 1 can cause a velocity u infinity at this position y is equal to h. So, that if a plate is kept here, plate will automatically be dragged with u infinity velocity. You have understood? Now, below a value of alpha is 1, that pressure gradient, or even without pressure gradient, one has to exert a force to drag the plate with a velocity u infinity in this direction, which will indicate that shear stress is positive here. So, when the value of the favorable pressure gradient, that minus dp dx, or the value of the alpha which you say is more than 1, then what happens? The velocity here, the shear stress changes its direction, negative. That means the drag force acting on this plate will be in the opposite direction, which physically implies, that means to maintain a velocity u infinity of the plate, this moving plate, we have to give a force in the opposite direction. Why? Because in that case the favorable pressure gradient corresponding to the value of alpha is equal to 2, 3 will cause a velocity at y is equal to h more than u infinity. That means if a plate is kept free, it will move with a velocity more than u infinity. So, that a retard force or a force in the opposite direction has to be kept to make the plate moving with u infinity, for which the shear stress direction changes. At alpha is equal to 0, there is no shear stress, there is no drag force required to move the plate. Now, similar fashion, if we see the shear stress distribution, that means tau yx at y is equal to 0, then we see at y is equal to 0, it will be the same expression, similar type of expression 1 plus alpha. Here also we see that so long in this regime, that alpha less than 0, so long alpha is greater than minus 1, what happened? Then alpha is greater than minus 1, this is positive. But when alpha is equal to minus 1, this is 0. That means the shear stress is 0, and alpha is less than minus 1, the shear stress direction changes. Why? Because the flow direction changes. So, here the change in shear stress direction on this plate means that there is a change in the flow direction, that is flow reversal takes place. So, up to alpha is equal to 0, the flow is in the positive direction, exactly, alpha is equal to minus 1, this is alpha is equal to minus 1. So, at exactly alpha is equal to minus 1, flow is 0. That means the fluid particle moves in this direction, alpha is equal to minus 1 is the point onset of flow reversal. That means this is the onset point of the flow reversal, after which if you increase the negative pressure gradient, the value of the alpha is lesser and lesser than minus 1, then the flow reversal will take place. So, shear stress will change its direction. So, this way we can find the shear stress distribution at the two plates in case of a co-ed flow. Now, another interesting feature comes for co-ed flow is this, that if we find out the average velocity, the average flow velocity or the flow rate. Now, in a co-ed flow, if you see, again I am drawing this. Now, in a co-ed flow, how to find out the, now this is x, this is y, this is y. Now, u by u infinity is y by h, okay, plus alpha y by h 1 minus y by h. So, it has to be kept in mind always, alpha is h square by 2 mu u infinity into minus dp dx. Now, to find out the flow rate, it will be u dy, that means we take an element, small element dy at a distance y. So, if this is dy, and if we take a unit depth in the z direction, in a direction perpendicular to the plane of the paper, so u dy 0 to h. That means, if I substitute this here, this function and integrate, you will get this equation half plus alpha by 6 into u infinity. If you just make the integration, it is very simple. I am not doing it here. So, that means u is equal to u infinity times this. If you substitute the value of u, the function, and integrate from 0 to h, you will get the value u infinity h half alpha plus 6. Alpha is the parameter which is non-dimensional pressure gradient. So, therefore, u average, average velocity in fluid mechanics is the flow rate divided by the cross sectional area, which is simply h, because we are taking unit depth in the z direction. That means in this direction, z, perpendicular to the plane of the paper. So, it simply comes half. Now, this gives a very interesting result. So, therefore, we see the average flow velocity or the flow rate is very much a function of alpha. So, the value depends upon the value of alpha, that is the pressure gradient, along with the value of u infinity and h. Now, we see one interesting thing, that when alpha is equal to minus 3, that is a advanced pressure gradient case. That means when dp dx is positive and its value is such that alpha becomes minus 3, then q is equal to 0 or u average is equal to 0. That means there is no flow in the positive x direction. This is a situation that there no flow takes place. What happens in this case? At any cross section, we have seen that when alpha is less than minus 1, the flow reversal takes place. So, alpha is equal to minus 3, the situation is like this. That means there is a flow reversal zone which is extended to a distance from the lower plate or the fixed plate, and there is a forward velocity zone. So, these two zones cancel each other. That means a local flow reversal zone takes place like this, a recirculatory flow takes place. So, the flow goes in the forward direction in the upper half, almost in the upper part of this thing near the moving plate, and the flow goes in this direction near the fixed plate or the lower plate. So, therefore, a local recirculatory flow takes place, so that there is no net flow in this x direction, where the flow rate becomes 0 or the average flow velocity becomes 0. That is one interesting fact. This is attained when the value of alpha is minus 3. That means this is attained for a given value of h, for a given value of u infinity, for a given value of mu, the liquid viscosity. In advanced pressure gradient, if you impose, that means which will be balancing the dragging effect, impose whose value equal to alpha is equal to minus 3, corresponds to an advanced pressure gradient. In the situation where this advanced pressure gradient is counterbalancing or counterbalance the dragging effect, then the dragging effect, that means the plate is dragged, some force is acted on the plate and the advanced pressure gradient both counterbalance each other, so that the net flow or the average flow velocity becomes 0. Well, now I will solve another class of parallel flow problem, which is plane Poiseuille flow, which is known as plane Poiseuille flow. Now, how do you define it? Plane Poiseuille flow is defined like this, that this is the flow between two plates, but both the plates are fixed, two fixed plates. In earlier case, the one plate was moving with respect to another. Here the two plates are fixed. Well, let us consider the distance between the plates be h. Now, when the two plates are fixed and we consider a parallel flow, parallel viscous fully developed flow. The word fully developed will be understood afterwards. That means the viscous force and inertia force are prominent. That means throughout the flow the viscous force is dominant. So, this is a parallel incompressible steady viscous flow. So, through two plates, we do two fixed plates. So, for the from the symmetry of the problem, we consider the middle axis that is the middle point, middle axis between the plates as the x direction, and we take this is as y. So, this origin. So, from at any point. So, this is x and y. Now, in this case, how do you derive the velocity profile? If you remember that for parallel flow, this is a parallel flow where u is not equal to 0, but v is equal to w is equal to 0. That means y component and z component velocities are 0, but u naught is equal to 0. Now, this type of situation we have always earlier derived, that if we consider a parallel flow where only one component exists, other two components are 0, and if we consider the z direction dimension is much larger compared to this y direction dimension, that means this h distance between the plates, then the final expression we can write like this. We get certain conclusion or certain result that u is a function of y only and pressure P is a function of x only, the direction, flow direction, and we get this relationship that mu d square u dy square is equal to dp dx. So, this was derived earlier, but I can again recapitulate it that this we get how. First of all, if we write the incompressible flow continuity equation in Cartesian coordinate, del u del x plus del v del y plus del w del z is equal to 0. Now, since v is equal to w is equal to 0, we can tell this is equal to 0 and then del u del x is equal to 0, all right. So, therefore, u is a function of y and z only, because u cannot be a function of x. Then if the z direction is so large compared to the dimensions in the y directions, so that the changes in u with respect to z can be neglected in comparison to change in u with y, so that we can write u is a function of y. So, we arrive to this corollary from continuity. Then if we look to the pressure, the Navier-Stokes equation in x and y direction, we will get this simplified equation. Let us first write the y direction Navier-Stokes equation, it will be better. So, u del v del x plus v del v del y plus w del v del z is equal to minus del p del y plus mu del square v del x square plus del square v del y square plus del square v del z square. If I write the equations for z direction, I will write in x direction at last. So, it will be u del w del x plus v del w del y, this is the inertial term or the acceleration per unit volume, w del w del z is equal to minus del p del z, the pressure gradient, plus mu, the same thing, Laplacian of w, del square w del x square, del square w del y square plus del square w del z square. Okay. Now, you see in two directions that v is 0. So, these all v w 0. So, in both the cases this is 0. So, the entire viscous term is 0, v w 0, which gives that del p del y is equal to 0. That means del p del y, from these two equations del p del z is equal to 0. That means p is a function of x only. So, with this, now if we write the x direction equation of motions, then we get rho u del x plus v del u del y, well, plus w del u del z is equal to minus del p del x plus mu del square u del x square plus del square u del y square plus del square u del z square. Here we see that del u del x is 0 from continuity, u is a function of y only, v 0, w 0. And here u is not a function of x, so 0. Now, among these two we have considered that u is a function of y, because z direction dimension is so large, so we can make it 0. So, from here we get mu del square u del y square. Now, p is a function of x only, so we can write it dp dx, and u is a function of y only, so we can write mu, well, we can write mu d square u dy square is equal to dp dx. That means this is the equation for any parallel flow where only one component of velocity exists. That means mu d square u dy square is equal to dp dx. Now, the argument is that u is a function of y only, p is a function of x only. So, therefore, the equality can only be valid provided d square u dy square and dp dx both are constant. That means p is a linear function of x, u is a linear function of y. Now, the next task which exists is now the solution of this equation, solution of this mu with respect to this. Okay, let me do mu d square u dy square is equal to dp dx. So, solve it. Now, simply if you make it the integration 2 times, we get 1 by 2 mu dp dx y square plus c1 y plus c2, 2 integration constants. So, we get straight away the profile for u. Now, the routine calculation is that you have to calculate c1, c2 from the boundary condition. What are the boundary conditions? boundary conditions, we have taken the coordinate axis this way, that means this is h by 2 and this is h by 2. So that at y is equal to h by 2, that means this plate u is equal to 0. Similarly, at minus h by 2, u is equal to 0. So, this is symmetric about this x axis. So, if you put this boundary condition, you get C1 0. So, from the first inspection, first time inspection tells that C1 cannot be there, because this is symmetric about this axis, x axis. That means there should not be any term containing a odd power of y. So, therefore, C1 has to be 0. But if you put it this boundary condition, you will also get C1 0. And C2, if you put any one of these boundary conditions, so you put C2 is minus h square by 8 mu into dp dx. So, this is the value of C2. So, now if I put this value of C1 and C2, I get the expression u is equal to h square by 8 mu. So, C1 is 0. If I put the value of C2, minus dp dx. So, minus dp dx is written in this fashion, 1 minus 4 into y by h whole square. So, precisely this is the expression for the velocity distribution for the plane positive flow. That means the flow is between two fixed plates, the distance between the plate is h. So, this is the expression where the coordinate axis is taken at the middle axis as the x axis, from which the y is measured. So, this is the velocity profile. So, if we put this velocity, well, you can see probably, I hope so. So, if we, if we put this velocity, plot the velocity profile. So, a number of velocity profiles or a family of curves can be drawn with this as the parameter. So, velocity profile is like this. But one interesting thing here is that u is 0 when dp dx is 0. Similarly, u is greater than 0 when dp dx is less than 0, and u is less than 0 when dp dx is less than 0 when dp dx is greater than 0. What does it mean? That when dp dx is 0, u is equal to 0, there is no flow when pressure gradient is 0. That means this flow is totally caused by the pressure gradient, because there is no other effect where the flow is caused. That means if there is no pressure gradient, there will be no flow. So, flow is possible only because of the pressure gradient. That means the pressure, depending upon the direction of the pressure gradient, the flow will take place. But in the earlier case, in the co-ed flow, one plate was moving. So, the external energy was supplied to drag one of the plates to cause the flow. So, therefore, in that case, even at 0 pressure gradient or an adverse pressure gradient, the forward direction flow was possible. But here, when the pressure gradient is 0, there will be no flow, and these two conditions implies that the flow takes place only because of pressure gradient and takes the direction of pressure gradient. When dp dx is less than 0, that means pressure here is high, pressure here is low, downstream pressure is low. That means a negative pressure gradient, the flow will take place in the positive x direction. Similarly, when dp dx is greater than 0, that means there is a negative pressure gradient, positive pressure gradient, that means the flow is higher in the downstream direction than in the upstream direction. So, therefore, flow will take place in the direction of favorable pressure force, that means in the opposite direction, that is the velocity flow is negative. So, therefore, flow velocity takes place depending upon the direction of the pressure gradient. So, pressure gradient is the sole cause of the flow in this case. Now, we go for the routine calculations of shear stresses and flow rate. Now, here if we want to find out the average flow, or average flow velocity, okay, this is the axis. So, this is x, this is y. So, this is the distance h by 2, this is the distance h by 2. This is the distribution of velocity. I am sorry, this is the distribution, the drawing is not that good, however. So, this is the middle point. So, therefore, we see that the velocity distribution u is equal to h square by 8 mu minus dp dx into 1 minus 4 y by h whole square. So, obviously, maximum velocity takes place at y is equal to 0. When y is equal to 0, u is u max. That means u at y is equal to 0, and its value is h square by 8 mu minus dp dx. And this is the diagram. So, maximum velocity is at the center line. So, therefore, u can be written in terms of u max as u max into 1 minus 4 y by h whole square. Now, if we want to find out the average velocity or from the flow rate in the similar fashion, so u average is equal to q by h, that means 1 by h. Q means the flow rate which can be found out integration of u dy, that means u max. I just put the expression of u dy. U max is constant, it is not a function of y. So, it is h square by 8 mu minus dp dx, which is a typical pressure gradient combined with h square by 8 mu. So, u max it has the unit of velocity dy, and it is integrated from minus h by 2 to h by 2 plus h by 2, because the axis is here. So, y is measured in this direction y. So, minus h by 2 to plus h by 2 cover the entire flow regime. So, if you do so, you will see that it will be coming 2/3 u max. That means, you take u max outside of the integration and you perform this integration from minus h by 2 to h by 2. So, then it will be coming 2/3 h will cancel. So, ultimately, you will find u average is 2/3 of u max. So, this is one 2/3 of u max. So, u max is given by this expression. Okay. Now, if we write the expression for shear stress now, if we write the expression for shear stress, what will be the expression for shear stress? Again I write u is equal to u max. In terms of u max, if I write, then it will be 1 minus 4 y square by h square. This is the expression. U max you can write h square by 8 mu into minus dp dx. All right. Now, you find out shear stress. It is mu du dy. All right. So, what is this? Minus 8 u max y by h square. 2y, that is 8y by h square. Now, if I want to find out tau at, for example, at the lower plate at y is equal to minus h by 2. So, what do we get? That h by 2, that means we get 4 u max. So, 4 u max by h. So, this is the tau. Sorry, tau is mu du dy. So, I am sorry, du dy is, there will be one mu into this u max mu by 4 u max mu by h. Now, we have already developed an expression with u average and u max, that u average is equal to 2/3 u max. We have already developed this. From integration of this, u average is q by h, 2/3 u max. So, u average is 2/3 u max. So, u max is equal to 3 by 2 u average. So, u max is equal to 3 by 2 u average. So, therefore, tau at the wall 1 minus y is equal to minus h by 2, one of the walls. Another wall y is equal to plus h by 2, the sign will be changed, the value of the tau will be all right. So, if I replace it, it will be 4 into 2/3, okay, mu into u average by h. Okay. So, sorry, 3 by 2, I am sorry, it is not 2/3, 4 into 3 by 2, u max is 3 by 2 u average. That means 6 mu u average by h. So, this is the value of tau w. Now, if a friction coefficient Cf is defined, this is known as Fanning's friction coefficient, which is defined as tau w by half rho u in. Here in this case, it will be defined as u average square. Now, in this context, I like to tell you, afterwards we will be discussing the pipe flow past bodies. So, this is a very good thing to remember, that when the past flow takes place over a body or within a duct, so we define a skin friction coefficient. This is known as Fanning's friction coefficient, which is due to the shear stress at the solid surface. So, this friction coefficient is defined always at this this fashion, the absolute value of the shear stress at the wall, because this is a scalar quantity without any sign, divided by the dynamic head, half rho into velocity square, and this characteristic velocity will be the average velocity in case of flow through a duct or channel. In this case we have taken the average velocity, but when there is a flow past a body, flow past a surface, then this velocity will be the free stream velocity. So therefore this is a general expression for the Fanning's friction coefficient, that this is the friction coefficient defined because of the shear stress due to the friction between the fluid and the solid surface, which is equal to the shear stress at the wall, that means at the solid surface, divided by the dynamic head based on the characteristic velocity, which is the average velocity in case of a confined flow, and free stream velocity in case of a flow past bodies. Okay, so this is the definition. So if with this definition, if we just now do mu average by h, and then half rho u average square, that means 2 will go, and rho u average square, then we will come to a value 12 divided by rho u average h by mu. So this is defined as Reynolds number. So Reynolds number, which will be discussed afterwards, Reynolds number. So Reynolds number, which is defined in case of a confined flow through the duct as rho mu, these are the rheological properties, density and viscosity, and numerator this is the characteristic velocity, which is the average velocity of flow, times the characteristic dimension. So Reynolds number is defined as rho times the characteristic velocity times the characteristic dimension divided by the viscosity. This characteristic velocity is the average flow velocity in case of an confined flow, and h, this characteristic dimension here is the h, it is actually the hydraulic diameter, which is defined as the cross-sectional area divided by the weighted perimeter. In this case it is h, so that the Reynolds number is based on the distance between the two plates, that means this is the distance between the two plates. So this is the Reynolds number. So therefore if we define the Reynolds number in this basis, we get the free. This is one very important deduction for a confined flow, that friction factor or this Fanning's friction coefficient, this is known as friction factor or friction coefficient, Fanning's friction factor or friction coefficient, or sometimes this is known as drag coefficient, skin drag coefficient, which is used in case of flow past bodies. Skin drag coefficient, there are different drag forces for flow past bodies that will be discussed afterwards. Skin drag, that's why it is known as skin drag. There is another kind of drag known as form drag, skin drag coefficient. So this is a function of Reynolds number only, and in case of a plain Poiseuille flow, this is plain Poiseuille flow. In case of a plain Poiseuille flow, this is 12 by Re. So this is one very important deduction, 12 by Re. So this is the, so we have derived the skin friction coefficient formula for plain Poiseuille flow along with the velocity distribution for the plain Poiseuille flow. So next class I will start the Hagen-Poiseuille flow, another class of parallel flow, which is the flow between a cylinder through a pipe. That means the area is fixed, but the cross-sectional area is a circular one. Okay? Thank you.